This experiment is a review of basic freshman chemistry apparatus and techniques, which includes using the electronic balance, hot plate stirrers, the pipette and burette, as well as volumetric flasks, and the basic benchtop spectrophotometer. Techniques used include a simple inorganic synthesis, vacuum filtration, dilutions, and a titration. So, with the data collected, calculations involving moles, molarity, stoichiometry, percent and theoretical yields, as well as limiting and excess reactants and dilutions can be completed. The theory, of course, is covered in general chemistry lectures. So students who have had predominantly freshman online, virtual labs or labs via videos will find these activities a quick way to get some hands-on lab experience with the important chemical apparatus and techniques shown here. Before beginning the experiment, first some background. The experiment involves a sequence of 3 simple chemical reactions involving copper-2 compounds. First, copper-2 sulfate is mixed with sodium hydroxide to yield insoluble copper hydroxide. This is then heated and converted to copper oxide, a black insoluble material that is collected by vacuum filtration and dried. The dried copper oxide is then reacted with sulfuric acid to reform the original aqueous copper sulfate solution. To begin, copper sulfate and sodium hydroxide need to be measured. The sodium hydroxide can be measured directly into a small beaker, placed on the electronic balance and set to 0. Then, according to the lab notes, approximately 1.2 grams needs to be measured out. Doesn't have to be exactly 1.2, but whatever mass you use needs to be recorded on your data sheet. Next, exactly 3 grams of copper sulfate is to be measured. This could be done in another small beaker, or it could be done in a plastic weighing dish, or on a piece of weighing paper. Your instructor will tell you if he or she has a preference. Let's use the weighing dish. It's placed on the balance, set to 0, and the copper sulfate is weighed out, needing exactly 3 grams. So exactly 3.00 grams of the copper sulfate has been weighed out, and that is now transferred to a 150 ml beaker. Next, the copper sulfate has to be dissolved. So the beaker with the copper sulfate is placed on the hot plate stirrer. A magnetic stirring bead is placed in the beaker, and approximately 40 ml of deionized water is added using a graduated cylinder. It doesn't have to be accurate. And then stirred. It just takes a few minutes at room temperature for the copper sulfate to dissolve. Once dissolved, the copper sulfate solution can be transferred to a 50 ml volumetric flask, which can be wet with water, but it needs to be clean. Place a funnel in the volumetric flask and simply pour the copper solution through the funnel. You can even allow the magnetic stirring bar to fall into the funnel, and then, very important, rinse the beaker with a little deionized water, but not too much because the total volume can't exceed 50. Pour that through the funnel. You can do that a couple more times. And then remove the funnel. Then fill the volumetric flask to the mark using a wash bottle. And mix.
Once the volumetric flask has been filled, a portion can be transferred to a spectrophotometer tube, which needs to be clean and dry, like this one. And you also need a blank, which is deionized water. Simply fill the tube with the copper solution. Rinse it, of course. If it is wet, wipe the outside, make sure that's clean and dry, and then you're ready to take the absorbance measurements. Your instructor will show you how to use your particular spectrophotometer model. Most benchtop UV visible spectrophotometers will be similar. A knob for the power, another for the zero adjust, a button to switch between absorbance and transmittance, and a wavelength knob to select the correct wavelength. For this experiment, select the appropriate wavelength as indicated in the lab notes. Begin the measurement by inserting the blank into the holder and adjusting to 0. Then the blank can be removed and the sample inserted. The absorbance can be read and recorded on your data sheet. At this point, the sodium hydroxide solution can be prepared. So here is the sodium hydroxide that was weighed into the beaker, and 10 mils of deionized water is added, again using a graduated cylinder. The mixture can be swirled until it dissolves. That can be set aside. Next, transfer back all the copper sulfate solution into the original beaker. The hot plate can also be turned on, about medium heat, and stirring bar added to the beaker. Transfer copper sulfate solution from the volumetric flask back to the beaker, making sure it's rinsed out with a little water. The volume doesn't matter because all the copper sulfate is going to be converted into copper hydroxide. So the volume of water doesn't matter. Also add the copper sulfate from the spectrophotometer tube, making sure that that also is rinsed out. And turn on the stirrer. While stirring and heating the copper sulfate, add the sodium hydroxide solution in a thick gelatinous precipitate forms. Continue stirring and heating while washing down any solution from the sides of the beaker. You'll also want to place a thermometer in the beaker, since the solution has to be heated to about 60 degrees. Right now it's just passing 40. So as it gets hotter and the reaction takes place, the solution will get darker and darker. It's now been heating for a couple of minutes. Temperature is 50 degrees, so it's approaching the 60 degree mark. The solution has now been heating for just under 5 minutes. All the blue color has disappeared, and now we can take it off the hot plate and begin the vacuum filtration. Don't forget that when you remove the thermometer, to rinse it with a little deionized water to get all the copper oxide back into the solution. And again, the total volume of the solvent does not matter. It's all going to be removed by filtration. Moving over to the filtration area, we have set up a sidearm filter flask, a Buchner funnel with filter paper, our solution to be filtered, and we're going to wash the precipitate with water, ethanol, and acetone. The amounts are given in the lab notes. The funnel is placed in the flask, making sure the fit is snug, and then the filter paper is placed inside the funnel. Use a wash bottle to wet the filter paper before turning on the vacuum. This helps it to stick on the bottom of the funnel. Begin the filtration by pouring the solution into the filter funnel. Try and keep it in the center at first. Note the colourless filtrate, indicating no copper ions. Continue with the filtration. Don't forget that the stirring bar is still in the beaker and you don't want that to fall into the funnel if you can avoid it. So, rinse the black copper oxide with your wash bottle and then transfer that back into the filter paper, avoiding losing the stirring bar. After rinsing out the beaker, there may be a small quantity of the brown copper oxide still on the magnetic stirring bar and perhaps staining the beaker, but that's okay. You might lose a very small amount of material that way, but once the copper oxide has been dried, it's going to be put back into the same beaker, so you can leave the stirring bar and the beaker as is. Next, wash the precipitate with some deionized water in several portions. Filtration process is very quick, so you can do that in fairly rapid succession. Now at this point you can turn off the vacuum and empty out the flask and discard the filtrate. This way you can separate the aqueous solution here from the ethanol acetone organic washings in the next step. Put them into a separate residue jar. Next, the ethanol. Again, that can be done in several portions. The idea, of course, is for the ethanol to wash the water from the solid. Then, next step, acetone washes the ethanol so that it will dry in the oven more quickly. Finally, we wash with the acetone. Continue with the vacuum for several minutes as the solid begins to dry out, and you can see it's beginning to crack here. Next step is to transfer it to the oven. So disconnect the hose, turn off the vacuum, remove the funnel from the flask and any rubber stopper, and take over to the oven. Place the funnel in the oven and make sure that it is labelled so you can identify it, and heat it for about 10 to 15 minutes until the solid is dry. While you're waiting for the copper oxide to dry in the oven, you can come back to your filtering flask and transfer the organic waste, ethanol and acetone, into a waste container. And you can also start prepping part C by collecting the reagents that you'll need for the titration and the apparatus. It can be assembled, the burette can be cleaned and filled with sodium thiosulfate solution. After about 10 minutes to 15 minutes, the funnel is removed from the oven. It's hot, so make sure you wear a protective insulating glove, and you can see the filter paper is curled up. The solid appears to be nice and dry. You can simply rest it in your filtering funnel to cool, and then next it's scraped out and weighed. The mass of the copper oxide needs to be determined. To do this, it can be transferred to a small beaker, or in this case a plastic dish. Place the vessel on the electronic balance, set it to 0, and then transfer carefully copper oxide from the funnel into the dish. The mass of the copper oxide is determined by simply placing the copper oxide back onto the balance and recording the mass on the data sheet. Note that a very small amount will be lost on the filter paper and a small amount remains in the funnel, but a very small amount, and this will be reclaimed when they are washed in the next step, when the copper oxide is converted to copper sulfate. Once the copper oxide has been weighed, it can be transferred back into the original beaker that holds a magnetic stirring bead, the one that had a little brown material on it. And small amounts that remain in the funnel and on the filter paper can be washed into that beaker. It may not be possible to get every last grain, but as much as possible. With all the copper oxide transferred back to the beaker, the next step is to convert it back into the copper sulfate by the addition of sulfuric acid. So the stirring bar is turned on, water is added, and 5 molar sulfuric acid. Volumes are given in the lab notes. Beaker is then heated to about 50 degrees until all the copper oxide dissolves and is converted into copper sulfate. You can see the blue colour forming almost immediately as the copper oxide begins to react with the acid. Use a thermometer to monitor the temperature to about 50 degrees, and it should just take a few minutes for all the copper oxide to dissolve and react. Once all the copper oxide has dissolved, it can be poured into a 50 milliliter volumetric flask. Beaker rinsed out as before several times. And the volumetric flask made up to a total of 50 mils. And shaken in preparation for measurement of the absorbance again. After the absorbance of the reformed copper sulfate solution has been determined, it's time to move on to the titration. Details regarding the stoichiometry of the reaction of the copper iodide starch titration are shown in the notes. The spectrophotometer tube containing the small amount of copper sulfate solution needs to be retained. That's going to be recycled. And the remainder of the copper sulfate solution, which is in the volumetric flask, is going to be transferred to a beaker from which the solution can be pipetted. This beaker needs to be clean and dry so that it does not dilute the copper sulfate solution. And then we can transfer 5 milliliters from the beaker to the flask for the titration. For this titration, a 5 milliliter graduated pipette will be used. A larger one, of course, could also be used. This particular one drains completely, so it'll measure exactly 5 milliliters. It is wet, so it will have to be rinsed with a small amount of the copper solution, which can be discarded, and then filled with the solution using one of these pipette syringes. To use the pipette, attach the pipette syringe to the end of the pipette, then turn the valve to draw the liquid up. When you've reached the correct level, you can then transfer the liquid and release it by pushing this drain button here. So first, we need to rinse out the pipette. Draw a little up. Rinse it, and then drain it into a waste beaker. Now we draw up 5 milliliters of the copper sulfate solution up to the mark, transfer to an Erlenmeyer flask. Allow it to drain out, touch the side of the flask. We've now transferred 5 milliliters of the solution ready for titration. Be aware that graduated or measuring pipettes come in two types. The one on the left, which can be drained completely to give, in this case, 5 milliliters, and the one on the right, which has a 5 milliliter marking at the bottom, and you can't let the liquid drop below that to give you exactly 5 milliliters. Before beginning the actual titration, the burette must be filled with the standard solution of sodium thiosulfate. In this case, 0.05 molar solution. Write down in your data sheet the exact molarity that you'll be using. Before you pour any solution into the burette, make sure that the tap is closed, and always use a funnel to fill the burette. Then you can add the sodium thiosulfate solution. So first of all, rinse it out with a couple of milliliters, swirl it around, empty it, then fill it up with the thiosulfate solution. Be careful when the level of liquid gets to the top of the burette. You don't want it to overflow. Fill the burette a little past the zero line, then open the tap and run the level of liquid down till it's right on the zero mark. One reason that is done is to ensure that there are no air bubbles in the tip of the burette, like you see here. So you can just keep opening, shutting the tap until the bubbles are gone. Then refill the burette if necessary until it reaches the 0 point. To begin the titration, some water is added to the copper sulfate solution and potassium iodide. Amounts are given in the notes. Immediate brown colour forms along with the precipitate. This is a standard starch iodine titration. begins with running in a few milliliters of the thiosulfate solution until the colour changes to a lighter orange colour, and then the starch is added for a clear endpoint. Now the starch is added, giving the characteristic blue-black colour, making the endpoint much easier to see. Continue the titration until one drop causes the dark colour to disappear. The endpoint will be observed when the dark colour changes to a white colour and a precipitate will be present. There are signs of the white colour appearing. And there's the endpoint. So the thiosulfate is stopped and the burette reading is recorded. Burette readings can be recorded to 2 decimal places. So record your actual burette reading on your data sheet. This particular value you see here is 33.80. But note, it is not the burette reading for the titration just seen. Your value will be quite different. So that's the one you need to use in calculations. So once you have the volume of the thiosulfate, you can use that with the information in the lab notes to calculate the molarity of the copper. For best accuracy, titrations should be repeated at least 3 times. So if time permits, your instructor may ask you to do that. The final part of this experiment is a simple dilution. Pipette 5 milliliters of the copper sulfate solution. This is the reformed copper sulfate solution that was originally in the 50 milliliter volumetric flask. Same concentration. Pipette 5 mils into a 25 ml volumetric flask. Dilute to the mark and then answer the question in the lab notes asking you to calculate the new concentration. Also measure the absorbance of this diluted solution and compare it to the absorbances of the reformed copper sulfate solution and the original copper sulfate solution. Finally, take all the copper sulfate solutions, including the portion that was in the spectrophotometer tube, and transfer them all to the copper sulfate waste bottle, which will be recycled by your instructor.